Hello and welcome to week 6 of the lectures on applied linear algebra. We studied eigenvalues, eigenvectors and how they provide a good understanding of linear operators, particularly with respect to repeated application of the operators. When you do a square and all that, they simplify the final expressions considerably. And we will see in this week 3 or 4 applications of eigenvalues and eigenvectors, particularly from an engineering point of view and also from various other interesting modern ideas as well. So, let's see, let's get started with the first one, which is about linear state space equations and system stability. This is a very commonly used model for many engineering systems, this linear system, state space system type model. We will see some very simple example. We will see how linear algebra comes in and how something called stability of a system can be measured using eigenvalues. So, let's get started. Okay, so this is a recap. The recap will remain the same for the whole of this week. The applications are varied. Eigenvalues, eigenvectors have huge number of applications. We will see a few prominent ones this week. Okay, so what is this system state and evolution? So typically when you have some, when you're building or when you're engineering something, it's usually a dynamic system in the sense that there are a few variables that capture the state of the system at any point in time, and as time evolves these variables change. This could be a mechanical system as something rotating, moving, etc. It could be an electrical system where a signal comes in and it gets processed, etc. So all engineering systems are like this. There are a few key state variables and these state variables evolve with time because of your actions, because of some environmental thing, and you want to keep tracking that as time progresses. Okay, so usually there will be a set of state variables, and this will so I will keep time discrete. It's like a discrete time system. Quite often people use continuous time models, but in this class that requires tools which are slightly beyond us. So we will use discrete time. So time goes as k equals 0, 1, 2, 3, etc. So this is not a bad model. Many systems today work like this. You have a discrete time clock, and every clock you take some action, you take some measurement. So you can have time quantized in this fashion. Okay. So this is my state variable, system state, so to speak. At time k, I will call it as a vector xk. I'll assume that there are n state variables, xk1, xk2, all the way up to xkn. Okay. So once again, I have a system, some engineering system, if you will. It has n state variables which describe it. At time k, these variables are denoted as xk, a vector xk, and these evolve with time as k increases from 0, 1, 2, etc. Maybe the initial state is known to us, and they evolve with time according to some equation that we control. Okay. So that evolution is controlled in a linear fashion. Okay. So we'll assume that there is a n cross n matrix A which will multiply xk to give xk plus 1. Okay. So this is not a bad model. Many systems evolve like this, maybe not in this exact simple way. Maybe A has some more complications, maybe there are some mild non-linearities, maybe there is some noise, maybe A itself varies with k. So you can do a lot of modifications to this model, but the essential simple model is xk plus 1 is A times xk. It's very popular. Quite often, if you look at, say, control systems, they would say state evolves based on the input also. Every k there will be an input which will also be included in the model, etc. But I mean, all of those are just artificial additions. As long as you have linear property, you can always redefine everything as one big state and write one equation like this. It's think about why that is true. So you can write like this. So this is xk plus 1 equals A xk. It's some sort of a linear model for evolution. So this is the model that we will look at in this lecture, at least, to study what happens when a system of with so many state variables evolves with time in a linear way like this. So what happens? What happens particularly as k becomes large and large and large and large. So that's what you want to see, right? So that's the part which we will look at. Okay. So like I said, so from k to k plus 1, the state variables get multiplied by the matrix A. Once again, remember, I am denoting the matrix, the vector in this form, but it's actually a column vector. Okay, so just for convenience, I'm writing like that. It's a column vector. Remember that. That's some notation we've been using in this class. So what will happen if you look at the time from 0 to k, the evolution from 0 to k, you will start getting multiplication, right? So you can see why, A times x0 will give you x1, and then you multiply with A again, you get A times x1, which is A squared times x0. likewise you will keep getting it. So, xk will become a power k times x0, and this x0 is the initial state. Okay. So, you see how this a power k enters the picture because of this kind of evolution, right. So, repeatedly this a gets applied to this the state of system variables, and then you get a power k. Alright. So, now we are interested in what happens to a power k for different types of a. Can we say something about a, and you will see naturally these eigenvalues will enter in a very nice way and determine what happens in this case. Okay. Okay. So, in particular there is this notion of stability which is quite popular in engineering systems: bounded input, bounded output stable in some sense. Okay. So, I say input here, but what I mean is bounded initial state and then bounded final state stable. Okay. So, I am just sort of abusing a bit of notation here to say input output. Okay. So, basically what it means is, if x0 is bounded, if the initial state is bounded, nothing is infinity extra, right, which is mostly what is going to happen, xk should be bounded for all k. Okay. So, I want to have this condition. If this is true, then this evolution, this a is supposed to be bounded input, bounded output stable. Okay. So, BIBO stable is a very common abbreviation in many engineering systems. So, this is a common requirement. So, now we will try to look at a and see when a will result in a BIBO stable system. So, what is the kind of consideration that we need to come up with. Okay. So, that is going to be the main objective of this lecture, and we will see the eigenvalues of a will nicely enter the picture and give you a good answer. Okay. So, this slide sort of captures the instability and the connection to eigenvalues. Okay. So, for what type of eigenvalues will you have BIBO instability? Okay. So, let us say you have an eigenvalue lambda for a with eigenvector v. So, we know that this AV is going to become lambda times v, right. So, if your initial state x naught is v, notice what happens, x1 becomes lambda v, right, a times x naught itself is v. So, AV lambda v. Then what will be x2? A squared into x naught, and that will become lambda squared into v, right, because it's a times a x naught. So, that is lambda squared times v, right. One more AV will come, AV is again lambda v, so we will get lambda squared v. So on, you see that xk becomes lambda power k into v. Okay. So, it is very easy, isn't it. So, you see how these invariant subspaces, one dimensional invariant subspaces help you when you want to look at stability, BIBO stability, right. So, we know that the thing is invariant, only this lambda matters, it keeps on getting multiplied, right. So, one thing we can conclude from this is evolution by a will be BIBO unstable if absolute value of lambda is greater than 1. Okay. So, this is easy enough to see, just let me just make sure I get this point right, it is BIBO unstable, right. So, that is the criteria we are looking at. So, clearly if absolute value of lambda, see I am imagining that lambda could be complex as well, even if a is real, lambda could be complex. So, that is why I put absolute value of lambda. If absolute value of lambda is greater than 1, and then you are allowed to pick the initial state to be this eigenvector v, which could also be complex. So, in general we will allow our numbers to be complex just to be safe. Maybe they are all real, maybe all that works out, but we will allow things to be complex as well. Okay. So, x naught is if you pick it to be the eigenvector v of an eigenvalue corresponding to an eigenvalue whose absolute value is greater than 1. So, you see clearly when lambda absolute value of lambda is greater than 1, lambda power k is going to blow up. Okay. So, when this blows up, for that input v, clearly you do not have BIBO stability. So, its stability is violated. Okay. So, if the modulus of any eigenvalue becomes greater than 1, then you have instability, absolutely, there is no problem here. So, what if this is not true? What if all absolute values of lambda are less than 1? Okay. Will you have stability? So, that is something we are yet to prove. We have only shown if there is an eigenvalue with absolute value greater than 1, then the system is going to be BIBO unstable. What if this is not there? What if all the eigenvalues are less than 1? Can we guarantee stability? Okay. So, here we need to look a little bit closer. Okay. So, we will start with the simplest case where A is diagonalizable. Okay. So, if your A is diagonalizable, remember just because you have an operator, it does not mean it has n independent eigenvectors and it always ends up being diagonal, right. So, there are cases where you do not have as many eigenvectors, so it may not be diagonal, but the diagonal case is the easiest to consider when you want to particularly raise it to higher powers, we know that for sure. Okay. So, if A is diagonalizable, we know that there is a basis of eigenvectors for A, okay, v1 to vn. and there are corresponding eigenvalues lambda 1 through lambda n. Remember, there may be repetitions here, okay. This lambda 1 through lambda n, I am writing it like that, but there could be repetitions, okay. So, remember that, keep that in mind. I am writing it for simplicity as lambda 1 through lambda n. So, any initial state x naught, since this eigenvector basis is there, I can write it as a linear combination of the eigenvectors, right. X naught, any initial state, in fact any vector v, right, I can write as a linear combination of the eigenvectors v1 through vn, okay. So, those coefficients I am simply giving them some names, some x tilde 0 1, x tilde 0 n, etc. Okay. So, the coordinates of x naught with respect to the eigenbasis I am calling as x naught x tilde 0 1 to x tilde 0 n. Okay. So, x naught may have other coordinates in the, I mean if you multiply this out, maybe you will get its coordinates in the standard basis, but I am interested in the coordinates in the eigenbasis. Once I write it like this, I can do repeated applications of A quite nicely, because I know each eigenvector is well behaved with respect to the operation A, right. Notice what will happen if I do x1, it is just A times x naught, it just gets multiplied by the corresponding lambdas. Next is x2, which is A squared x naught, and then it gets multiplied by lambda 1 squared to lambda n squared. So, that is it. So, you can keep on doing. You see the kth state at the time kxk is simply the same coordinates, but instead of v1 I would have lambda 1 power k v1, and instead of vn I will have lambda n power k vn. Quite easy to see, okay. So, we see interestingly, if absolute value of lambda I is less than 1, right, for all I, then I will have BIBO stability. In fact, it will be, xk will always tend to 0, right. Eventually, as k becomes very large, it depends on how close lambda I is to 1, etc. But if it were to be less than 1, the absolute value, if it is less than 1, then each of these terms will tend to 0 and you will have stability. If any of them is greater than 1, then we also know it will be unstable. But if it is less than 1 and A is diagonalizable, clearly easily we are able to see that this is this will have this kind of behavior, right, lambda 1 per k, lambda n per k. And you can imagine what else can happen here. What if absolute value of lambda is equal to 1, right? In that case, you can have more interesting behavior, right? Some of the eigenvectors will not vanish; they will continue to stay there as and when whatever happens, how many ever times A appears, right? So all those kind of things will happen. Interesting behavior like that can be observed if absolute value of lambda is equal to 1. So you will have some oscillatory or such behavior which is possible. But if lambda I is less than 1, then everything will go to 0 eventually. If lambda I is greater than 1, there will be some inputs for which you will get blow up. Okay, so that's what happens. Most inputs will also end up being like that. Okay, so good. We've seen two different cases. One where you have instability because eigenvalues greater than 1, then you're blowing up, and you have stability when A is diagonalizable and absolute value of lambda is all the eigenvalues are less than 1. Okay, so you see this absolute value of eigenvalue, absolute value of the eigenvalue, okay, controls stability in these kind of linear state space systems. Okay, so that's a good result to remember. Okay, so it's a wonderful application of eigenvalues. There are so many systems out there, and all of them should, for stability, have eigenvalues control. Okay, that's a good thing to know. So what if it's non-diagonalizable? I want to give you a few examples for what happens in the non-diagonalizable case and point you to a powerful result which helps you capture all the non-diagonalizable cases also. We won't quite see a proof of this result, but it's interesting to know this result at least. Okay. So let's take non-diagonalizable cases. We'll start with very simple examples. Okay. So the example I'll start will be the 2 by 2 case, one of the simplest cases of a non-diagonalizable 2 by 2. Right. So you have lambda on the diagonal. The lower value is 0, and then you have 1 on the upper value. Okay. So there are 2 eigenvalues here and there is only one eigenvector. Okay. So we have seen this before. Okay. So we have seen such examples before. This is not a diagonalizable case. You don't have enough eigenvectors as many as the multiplicity of eigenvalues. Okay. So now what happens to this when you keep raising it to higher and higher powers? You can do this proof. It's not very hard. You can show A power k is lambda power k on the diagonals. But it will have a non-diagonal value also. It will have k times lambda power k minus 1. Okay. You can prove this, for example, by induction. It's not very hard. You just do a k you can go to a power k plus 1. You just multiply by a on the left, for instance, or the right. You will see you will have lambda power k plus 1 on the diagonal, and this one will become k plus 1 times lambda power k. So, you can see how that is set up. It will come out quite easily. Okay. So, you might argue, what about other 2 by 2 cases which are non-diagonalizable? So, it turns out this is a very typical case for 2 by 2 when it is non-diagonalizable. There is no other case really, right. So, see, the two eigenvalues have to be the same. So, you know that I can make A into a upper triangular matrix with lambda here, and then this value, can it be something else? Not really, right. If you think about it, you can adjust so that it becomes 1. So, think about how you do another basis transformation to get 1. Okay. So, it is not as simple as row elimination. You need a careful invertible matrix multiplication on both sides and change the basis to get this. Okay. So, it is possible. So, this is you do not lose any generality in the 2 by 2 case. Okay. So, that is good to know. So, this is nice. Okay. I mean, I was not really going into detail there, but I am just saying that this is enough. You do not need anything more. What about 3 by 3? So, once again I will consider a very simple case. Okay. So, I will consider in the 3 by 3 case, I will consider a case where there is lambda, lambda, lambda on the main diagonal. Below that is all 0. I know I can take it like this, upper triangular is okay. But on the upper part, I will only take 1 on the next immediate diagonal and then 0 after that. Okay. So, I will only consider a case like this. So, we will see later why these kind of things are enough. Okay. But for now, just believe me, let us handle this case first. Okay. So, this seems to be a simple case, and if we can't handle this, it's very unlikely we will be able to handle other things. So, we will handle this case first. So, once again there are 3 eigenvalues, as an eigenvalue lambda repeated thrice, but there is only one eigenvector, right. So, there is only 1 0 0, there are no other eigenvectors. So, once again if you do a power k here, this is again a proof you can do by induction. You can sort of see how this generalizes from the previous one. You will have lambda per k on the diagonal, and then you will have k lambda per k minus 1 on the slide 1 off diagonal, and then the next one will be summation up to k minus 1, then k minus 1 into k by 2 plus n. So, you can see why this is true. You can sort of multiply and check by induction that this will give you the correct formula going forward for a power k. Okay. So, this is a proof that you can do. Notice the important thing here is, okay, so quite often you want exact expressions, but the point here is this one, this function is less than or equal to, let us say, k squared by 2, okay, isn't it? It's some k minus 1. So, in fact, if you do not like even k squared by 2, you can say it is less than or equal to k squared. So, something into k squared. Okay. So, this detail, this k minus 1 into k by 2 is sort of is confusing to us. What really matters is it grows like k squared, Okay. There could be some constant there, half or something, but it grows like k squared. Okay. So, there is this convenient notation for functions like this. There are these class of functions, okay, which are all upper bounded by some constant into k squared. Okay. So, we will define this class of functions, and this notation is very common, big O of k squared. Okay. What is big O of k squared? This represents the class of functions. It is not one function, it is actually a class of functions. There are many functions which satisfy this upper bound less than or equal to c k squared, usually for large enough k, but even we do not even need that for this large enough k. Okay. So, this is how people define this big O of k squared. Even though for small k there may be some skirmishes here there, once k becomes large, this function is upper bounded by c k squared. Okay. So, that is big O of k squared. So, it is very common to write this instead of writing k minus 1 into k by 2, I might as well write like this, right, k into k minus 1 by 2 lambda per k minus 2 seems very confusing. I can write it as big O of k squared lambda power k minus 2. So, you get a sense of what it is, right. So, this is how this is used. You get a sense that k squared is sort of the dominant term in this term. I do not really bother about the details of how that term is. I just need to know that it is order of big O of k squared. This is called big O, by the way, big O. Okay, so big O notation. There's similar small O notation and all that. We don't need that as of now, but right now this big O is a useful thing to quantify things like this. Otherwise, you will be worrying so much about the exact expression here, but while it's not so important to you in the study. Okay. So this is a power k for this case. Okay, can I generalize this? It turns out yes. Let's take a slightly bigger example, 5 by 5, and once again I'll take a very simple form where lambda is on the diagonal 5 times, and then there is just 1 showing up on the 1 off diagonal. Okay, so this is not needed. Just remove it. So there are 5 repetitions of lambda. There's only 1 eigenvector, and what can we say about a power k? So once again, a power k, you can do a very careful count and find these exact functions if we want, but it's really not needed. You can use this wonderful big O notation that we have found to simply write, the first on the diagonal you will have lambda per k. 1 off diagonal you will have k times lambda per k minus 1. That's okay. In the second diagonal, the next diagonal, you will have some function of k squared. You know exactly what that function is, some k into k minus 1 by 2 or something like that. But I am just simply writing it as big O of k squared. In the next one you will have k power 3. Okay, so that you can also find out what that is exactly if you want to. If you put in some effort you will get it, but that's not so important to us. All that matters is it's big O of k power 3. And the next final thing will be big O of k power 4 lambda per k minus 4. Okay, so you can prove this, you can prove it by induction or various other methods are there. You will get this answer. Okay, so the point is a power k has these kind of terms, k power 4 into lambda power k minus 4, and then lambda power k, lambda power k shows up, and then k power something shows up. Okay, so this is what happens for matrices of this form. Okay, so lambda on the diagonal and ones on the off diagonal. Okay, so you might rightfully ask, what about other forms of this matrix? Right now this thing looks so restrictive. What about other forms of this matrix? So it turns out there's a very powerful result in linear algebra which says that these kind of things are enough. Okay, so what is that result? That result is what is called this Jordan form for any matrix. Okay, so it turns out whatever the matrix may be. Okay, so whatever non-diagonalizable, diagonalizable, general case, any matrix A has something called the Jordan form. Okay, what is this Jordan form? You can write it in a block diagonal structure like this, A1, A2, Am. Okay, each Ai is a Li by Li matrix. Okay, so square Li by Li matrix, and this n, which is the overall number of columns or rows, is simply L1 plus L2 plus Li. Okay, and what is each Ai? The form of each Ai is either lambda I if Li is 1. Okay, it's either lambda I if Li is 1, or if Li is greater than or equal to 2, it has a form that we have been assuming so far, which is lambda I appearing on the diagonal and just once appearing on the 1 off diagonal, everything else is 0. Okay, so once again let me repeat myself, every matrix or any matrix, diagonalizable, dot diagonalizable, whatever, has something called a Jordan form. What is the Jordan form? There is a basis in which it becomes block diagonal, and every block is either a 1 by 1 lambda or a Li by Li, this simple form we have assumed. Okay, lambda showing up on the diagonal and 1 showing up off diagonal. Okay, now these lambda i's may repeat. Okay, they may repeat in across these Ai's, but the form will always be like this. You can always write it like this. Okay, so this is a fantastic result, and this uses ideas called generalized eigenvectors. If we have time later on in the class, we'll come back to it. But for now, let's assume this and see what it means for our result. So once we know this, what happens now? A power k will simply become A1 power k, A2 power k, Am power k, right? I don't need to bother about anything else. Okay, because this is block diagonal, right? When you multiply, you will simply get A1 power k, A2 power k, Am power k. So the only thing I have to worry about for a general matrix A when I raise it to the power k is matrices of this form, and of course constants just 1 by 1 matrix, they just go up, not constant, I mean scalars, just lambda I that raised to the power k is simply that raised to the power k, and matrices of this form raised to the power k, which I already know how to do, right? I did it for the 5 by 5 case, you can easily extend that to the general case, right? So that is possible, alright. So now values of a power k will always be of this form, k power Li minus 1 lambda I power k minus Li minus 1. Okay, so this is the form for values of a power k, the non-zero values. Okay, so we see that if lambda I, absolute value of lambda I is less than 1, these values will tend to 0 ultimately as k tends to infinity. So you will have stability. Okay, so this is a result you might quote, but I mean you might want to be careful, because there is this k power li minus 1, and if this li is very large, right, even if lambda I is reasonably close to 1, this may not die down that fast. Okay, so you really might need a very large k before it dies down. So something to worry about, but still asymptotically, at least as k becomes really large, this will ultimately become stable. Okay, so this Jordan form is quite useful for these kind of results, but we will not see it immediately. We will come back and see it later. Okay, so to summarize, we have seen that if an evolution is linear with an operator A, then the eigenvalues of A, the absolute value of the eigenvalues of A, control its stability. Okay, so if the absolute value is less than 1, you end up BIBO stable. If it is greater than 1, you are not BIBO stable, it can expand. Equal to 1 is a case we did not consider, it results in some oscillatory type behavior. Okay, so that is the end of this lecture. Hopefully you are convinced now why eigenvalues are so widely used in engineering, in systems. They play a very central role. There is an equivalent expression for continuous time as well, but we are not going into that in this lecture. Okay, thank you very much.